people might still keep rolling in. I'm Sean Cummins. I'm a principal SE with the Enterprise and Mid-Range Systems Division. I tend to focus a lot on VMAX, on VNX, and VPlex as well. But I'm going to talk to you today about some advanced SYMCLI scripting and where traditional scripting techniques are appropriate, and then where some perhaps some alternate approaches are appropriate, where you use XML and other advanced programming languages like Python or a Perl or a Ruby. We did this a couple of years ago in Python and XML. This year I ported it, Perl and XML. This year we ported it over to Python. So my goal for the end of the session here is hopefully that you'll be able to understand and use the built-in SYMCLI filtering mechanisms. And if you've been around SYMCLI for a while, you probably are already aware of them. I'll just talk about a few of them. And in cases where there are not a built-in filtering mechanism for the objective you need to achieve, I'll talk a little bit about how you can kind of roll your own filtering mechanism by just piping things to standard shell utilities like grep and awk and that sort of stuff. Then we'll talk about where that kind of thing, that approach can kind of break down, where it can be a little bit less resilient over time, and other approaches that are more resilient over time, specifically the XML output and things like Python and Perl and Ruby or whatever you happen to choose. And at the end, we're going to create a custom script using Python and the XML output of SymCLI. It's going to do a specific function, but you can use it as kind of like a skeleton. You can use the function in there to create your own XML objects inside of Python and write your own reporting scripts that mine data out of SymCLI's XML output. So just, if you've been around SymCLI for a while, I'm guessing a lot of you have, if you've decided to come to this session, you've probably noticed that the structure of SymCLI is kind of similar to Unix in nature, where you've got lots of different commands that are kind of oriented towards one specific type of task. And of course, each command has lots of different flags and arguments and that sort of thing. And it's similar to Unix in that you've got lots of different tools that are oriented to doing one type of task. And you can kind of string these things together where the sum of the whole ends up being greater than its parts. And that's kind of what the shell scripting bit of this is. And of course, you can schedule it, right? You've got your built-in OS schedulers like your cron or your scheduled tasks if you happen to be doing this on Windows or some kind of enterprise scheduling mechanism. But before we start, just some kind of tips, pointers. Make sure you understand the SymCLI in general before you start automating something. Know the flags and what the expected outputs are going to be for various commands. If you're going to try to write a script, you might want to also explore, the capabilities of Unisphere or something else that you already have in the environment, just to make sure you're not reinventing the wheel. Just make sure that functionality doesn't already exist before you start rolling your own thing. Use what you know, right? I'm using Bash and I'm using Python because that's what I'm comfortable with. But like I said before, we did this in Perl before. I'm actually doing ZSH, but it's backwards compatible with Bash anyway, so anything I do shell-wise here will work in Bash as well. No shame in borrowing, right? There's a lot of code out there already. Just Google it up, and you'll see that a lot of people have already done SymCLI scripts. Some of them have made them public on places like GitHub. So you can reuse some of that code out there. Or even if you're trying to do something that is not SymCLI specific, you'll often find that the task that you're trying to achieve, someone else has done before something similar, right? And you can just kind of reuse their code and modify it for your own purposes. This is important to me. It probably is for everyone. Code with reuse in mind, right? So over time, you want to write things in functions and classes wherever you can. And over time, as you write these things, you'll kind of build up your own library of scripts that you can use. And as that grows, you'll be able to do more in your scripting endeavors. And then probably the most important thing here, we're dealing with VMAX, right? These are hyper-consolidated mission-critical systems. Even if you're standing at a keyboard and doing configuration changes, you can do a pretty good amount of damage if you mess something up. But once you start automating something that is going to be making changes on a system, that can do a whole lot of damage in a very short amount of time. The scripts run, of course, very quickly. So make sure you test these things extensively before you deploy them. Hopefully you've got at least a portion of the storage in the array that you can test with. If you're really lucky, maybe you have a test dev array or something that you can test with. And make sure you've got the logic in there that can react to failures. Check those return codes and react to them appropriately. So first, we're going to just start kind of on the basic stuff and move deeper. And this is SymCLI one-liners. So just basic filtering that's built into SYMCLI at the beginning here. So this is the symdev command, right? So this just lists all the devices in a particular storage array, assuming you add the SYD flag. And there's a lot of filters built into this command, and really all of the commands. And so as just an example, say we went to list all of the unmapped open system devices that are not BCVs and RTDevs, and we want to skip meta members. So we use these flags. We use no port to show the devices that are not mapped to FA ports. Emulation FBA is fixed block architecture, so open systems devices. TDev shows only virtually pooled devices, TDev devices. No BCV skips BCVs. It's not going to skip clones. It will skip devices that are explicitly tagged as being BCVs, though. No member, that's a relatively new one. I think we added it around solutions, I believe, were 7.4 or so. And that will skip printing out meta members. It'll only print out meta heads, so it can be pretty useful. And this is just the output of that, right? So you see all the devices that match that category. Another one, just taking this a little bit deeper, say we only want to see devices that match those previous filters, but we also want to add a capacity filter. We only want to see devices that are 17,265 megabytes. Well, we add the cap flag, and we do 17,265. And we see of that previous list, there's only 3 devices that are that size. So just moving on, breaking, getting beyond where there are filters in place. Say you want to see a list of all the gatekeepers in a particular array. There's no built-in filter for that. So we're going to kind of just roll our own. This is a relatively simple example here. We'll do a symdev list. So it's going to dump out all the devices in the array, right? And then we're going to use grep and a regular expression to match 3-cylinder devices. And that minus E on the grep, it just means what's going to follow is an extended regular expression. The regular expression functionality that's built into standard grep is relatively limited, but it's enough to do what we need to do for most tasks. In some cases, you might need to break out a set or something like that. But just kind of going over this, we're looking for 3-cylinder devices. So what we're going to look for is a 3 preceded by a space and ended by the end of the line. So we've got a space in there, we've got a 3. The $ is just the regular expression syntax to match the end of a row. So it matches what I've highlighted there. It matches the entire row that contains what is highlighted. What you'd most likely want to do is filter out gatekeepers rather than filtering in gatekeepers. So if you just add the -V flag to the grep, it just kind of reverses the polarity of the grep. Another one here, we're switching to a different command. This is the symcfg list tdev command. So this command, of course, will give you detailed information about all of the provisioned tdevs, like the provisioned capacity, the written capacity, the allocated capacity over pools. But in this case, we want to get a feel for what devices on a particular array are or are not being managed by FastVP. So what we're trying to find out is we're looking for devices that have multiple allocations. And typically, the main thing that is going to cause a device to have allocations in multiple pools is going to be FastVP. There are other side considerations that could cause this to happen. So say you had a device that was associated to a policy, and it did some promotions and demotions and distributed things around, but then you deassociated it to a policy. This would still show up here, even though it's not actively being managed by Fast. And there's a couple other things, too. But generally speaking, this will give you a good idea of what devices are or are not managed by Fast. And what we're doing here is just pattern matching. So you can see the output of this command right here, the symcfg list tdev gb. We're outputting that output, or piping that output to a grep again. We're doing grep -E, so what's following is an extended regular expression. The extended regular expression in this case is searching for a specific flag pattern over here. So really the flag that we're looking for is the X. I don't want to search for just X, because X might show up somewhere else. Like if they have a pool with the X in the name, I don't want to accidentally match the X there, but I don't want to match the pool. I want to match this flag specifically. So I'm going to search for the entire flag pattern. And what I'm doing is I'm searching for FX period B. So the F just means that it's an FBA device. The X, like I said, that means that this device does have multiple allocations. That's specifically what we're looking for. The period just means that there are persistent pre-allocations on that device. So somebody pre-allocated extents on the device and did it persistently. And I have an escape in front of that period, because if you don't escape out the period, then it's treated as basically a wild card. A period in a regular expression is a wild card. It'll match any character. And then the B just means it's bound. So that will match all of these devices here. And we know that all of those devices likely are, or at one time were, managed by FastVP. So we're moving on a little bit from just these basic filters into kind of stringing one SYMCLI command, the output of one SYMCLI command, into another set of SYMCLI commands. And we do this with just standard Linux shell scripting, right? So we basically take that output, pare it down to just what we need to be the input into the next command, which is generally going to be a list of something, like a list of devices or a list of disks or a list of DAs or FAs or something like that. And then we iterate over that list. And as we iterate through, we treat every element on that list as input into a next command. So I'll give you a couple examples of that. So in this one here we want to show all of the FA mappings for all of the devices that are in a specified storage group. And a reason that you might want to do this is, say, you've got a storage administrator that's dealing with a front-end imbalance problem where they've got too many heavy-hitting hosts that are just sharing, say, 4 FAs, right? And those FAs are very highly utilized. You've got queuing going on, that kind of thing. So you need to move some of those heavy-hitting hosts off of the highly utilized FAs onto a set of lower utilized FAs. So the way we would do that is you set up another masking view, have the same storage group in there, the same initiator groups in there, but have a different port group in there. So that would cause these devices to be mapped to another set of FAs, present that second set of FAs to the host, validate that they're visible, and then we can tear down the old masking view, take the old paths away. But if when we tore down that old masking view, we didn't use this unmap flag, then we're going to leave orphan mapping records of those devices to those same FAs. And there's a limit to how many mapping records you can have on a particular FA slice. It's 4096. So it's possible, if you're not using unmap, that you could potentially in the future run into this limit. And what you would want to do is go back and identify these orphan mapping records and then remove them. And this gives you a way that you can do that, identify that and do it. So 2 commands are going to be required to do this. The symsg show command is going to give us the details about a storage group and the members of that storage group. And then after we have the members, we're going to do a symdev list on every one of those members to get the front-end mappings for that members. And then we're going to summarize it and print a report. So here it is. Here's actually, before we start automating it, I'll just explain how to do it manually, right? So here's the symsg show command on the left. And you can see here we've got our one storage group name, WST35. And if you look further down in that output, we can see those 4 devices are in that storage group, right? And we then know that we need to execute symdev lists 4 times, once for every one of those devices. So we do that over here. So here's the symdev list for device 23.7 Charlie. And if we look down in that output, we can see that this device is mapped to those 4 FAs right there. So ultimately, we need to do that 4 times. We have to do the symsg command once, and then the symdev list command 4 times. So 5 commands total for this particular storage group to accomplish this manually. So how would we go about automating this? The first step is going to be taking a look at that first command and paring down its output. So the only thing it outputs is the 4 devices, the members of this storage group. So the way we would do this, or the way I would do this, there's more than one way, do the symsg show and the storage group name, pipe the output of that to, again, a grep statement. And this grep statement is, again, going to be a regular expression. This regular expression is a little bit more complicated, but it's not too bad. Basically, what we're looking for here is a 4-character hexadecimal string. So a Symmetrix device ID, right? They're generally going to be 4-character hexadecimal strings. So just breaking this down, we've got a caret at the beginning. Caret just means begin at the beginning of the row. So, column 0 in the row, right? The \s star means match 0 or more spaces. So what is to follow that \s star could be at the very beginning of the line, or it could be anywhere after 0 or infinite spaces, right? So it could be all the way at the end of the screen. In this case, it happens to be indented a little bit, so we did actually need that space there. After that, we've got in these square brackets character class. And what that character class just means is we're going to match 1 character that is between 0 and 9, lowercase a through f, and uppercase a through f. And it just matches one of them. But then after that, in curly braces, we have a 4. So that means match 4 of the previous character class. And I've got the curly braces escaped out, so the shell doesn't interpret them, but so grep interprets them. So that's how I match those 4 rows that contain the Symmetrix devices right there. And moving on, we pipe that to an awk. And the only thing I'm doing with awk is the print $1 to extract the first column out of that, the matched rows. Okay, so moving on, that's got to be, we got to iterate against that list now, because what we have is basically a list of devices, right? So we have to iterate over that list, and for every device in that list, we have to execute the symdev list command to get the FA mappings for that device. So to iterate over it first, what we do is we have our previous command in there, we enclose it in parentheses and precede it by a $. And what that means is it turns it into basically a list, an iterable that the for loop will be able to iterate against. And then we see we start our for loop here. We have for dev in. The dev is a variable. So every time we iterate over that list, that dev variable will become the next device that we want to work against. Then we start our code block with the do statement there, and there's only one command inside there. It's symdev list -dev $dev multiport. So the $dev is where we're going to replace that variable with the actual device that we're working on that time through the loop. And then the multiport flag is going to show us all of the FA mappings for that device. So your output ends up being this. You get 4 full screens of data. So it is the information you need, but it's a little bit more information that you need, right? So what can we do to kind of simplify this, condense it to just the FA ports that we want to see without duplicates and without the extraneous information from the rest of the human readable output? What we can do is we can just keep going on, right? We can, inside of that for loop, in the code block there, where we had that multiport flag right afterwards, we're going to pipe the output of that to a grep visible, and the grep visible is going to match these 4 rows right here, which happen to have the FAs on them. And then we're going to use awk again and extract the 4th column, so we just get the FA mappings. And at the very end, what we have is a sort -u, and that's outside of the for loop. So inside the for loop, we're going to print that list of FAs 4 times, but then we're piping that to the sort -u. The sort -u is going to sort all of that output, and the -u is only going to print unique entries out of that output. So what you end up seeing is this. And we can see that all 4 devices in that particular storage group were only mapped to the same set of 4 FAs. So if that makes sense. So you could then compare this to your masking view for this particular storage group and see if there's differences there. Say there's 2 extra FAs in this output versus what you have in the port group for the masking view. Then you're potentially in a situation where you have orphan mapping records for that storage group. And you can go back and resolve them. Another example here is draining TDATs from a disk. So a scenario where you might want to do this is, say, you've got a back-end imbalance on your SIM. So you've got maybe too many EFDs on a particular DA slice and not enough EFDs on another DA slice. So you have to take one of your EFDs out and move it to another DA, so you balance out the EFDs across the back-end DAs. But of course, before you take a drive out of a box, you got to make sure there's no data on it, right? And the way to get the data off of it is to do a deactivate and a drain on all of the TDATs on a specific physical disk. So here's how we do this. So on the right, we're seeing the output of this command, symdisklist, DA, interface, target ID. That's how we specify a particular physical disk. We add the -hypers and the -verbose flag here. And what we see is all of the TDATs that are on that particular physical disk. Right? So, and then we pipe that to a grep. And again, we're grepping for, well, here we're grepping for FBA, because that happens to be a unique entry that's nowhere else that will match the TDATs on the drive. And then we use awk to, again, extract the 4th column. So that's our list that we're then going to iterate against, again, in a for loop. So here's our for loop. Again, we took that previous command and we surrounded it by parentheses and preceded it by a $sign that makes it a list, an iterable that the for loop can iterate against. We've got for dev in. So again, dev is going to be our variable here that changes every time through the loop. We begin our code block up here. And really, there's only 2 commands inside the code block. There's 2 echo commands. And those 2 echo commands, the first one echoes the deactivate commands that are necessary for symconfigure to deactivate that particular symdev. And we just redirect that echo into a file called deactivatecommands.txt. And we do the same thing for the drain. We do the start drain on dev, $dev. So that's the syntax for draining a device after it's been deactivated. And we redirect that to the drain commands.txt. So now we've got these 2 text files, right? Their contents are here. You've got the deactivate commands on the left, the drain commands on the right. Executing these is just a matter of any other symconfigure command where you're executing against a file. You're probably already familiar with the syntax here. So this starts it. Then you're probably going to want to monitor the progress over time, right? And a way to monitor it here, you've got this command, symcfg list gigabytes data dev, and then you list out the TDATs that you started the drain on. And if you just execute this periodically, you'll see that the usable or the used gigabytes and the full percentage will go down over time. And you can just wrap a while loop around this to kind of pull periodically as well. That's what I did here. So I did while true do symcfg, the whole command. And I entered a sleep 10. So it waits 10 seconds, and then it goes back to the beginning of the loop and executes it again. So it'll just constantly poll, and once it gets down to 0, you can hand off to your customer engineer and have him pull the disk out, move it to where it needs to be, and do his bin file, right? So everything we've talked about so far has been, it's been about the human readable output, right? It's been basically screen scraping what you as an administrator would expect and see from a normal SYMCLI command. But this approach, while it will work for like an ad hoc type of thing, it can be inherently brittle at times, because you think about what happens when you upgrade your version of Solutions Enabler and new features are added to the VMAX, and that requires, say, new flags to be added, or it requires that the output has been rearranged slightly on the screen. Those patterns and regular expressions that you were searching for before don't work anymore. So you could potentially break your scripts if you upgrade Solutions Enabler and your screen scraping, your scripts are screen scraping. And here's just an example of that. So say we did that previous command where we were looking for multi-pool allocations before, and we developed that on Solutions Enabler 7.2. Now on Solutions Enabler 7.2, and remember when we did it, there were 4 columns. There were 4 flags in the flag column. But in Solutions Enabler 7.2, there were only 2. There was FX. So if we wanted to search for FX, we'd have our command. We'd pipe the output of that command to a grep, and we just search for space FX space, right? But then we upgraded to Solutions Enabler 7.6, and new features were added. New columns were added to that flag column. Now the output is FX period B. So that previous grep statement, which is looking for just FX, it's going to be broken. And anything that depends on that grep statement to work is also going to be broken. And that could be quite a bit of stuff, right? So one way to fix this, if you've already developed it this way and you're already doing the screen scraping, and you ran into this problem or other problems like it, there's a lot of stuff built into Solutions Enabler that is for backwards compatibility. Things like you can continue to use symmirror commands against VCVs, and we'll translate those symmirror commands into the necessary symclone commands so it doesn't break old timefinder mirror scripts. Things like symmask commands that you can still execute on a VMAX. Well, VMAX doesn't do VCM. It doesn't really do symmask anymore, but we'll translate old symmask commands into symaccess commands and access logic. This is something similar, just one of those many things. It's called compatibility mode, and what compatibility mode does, it just changes the output for newer versions of Solutions Enabler to emulate older versions of Solutions Enabler. So 7.6, which is the latest, you can go back to version 7.2. And to do it, there's 2 ways of doing it. One way is you can do it globally, right? You set an environment variable, and that environment variable is right here, SYMCLI mode equals v72. And if you do it globally, then any command you execute from then on will emulate the older version of Solutions Enabler, whatever you specified. You can also do it ad hoc. So on a particular command, just add this flag here, this mode v72 flag. And that will change that particular command's output to just emulate the old version. So here's an example of that with that previous script, right, where we were looking for the FX on the right. That's our old 7.2 output. And I'm doing that old 7.2 output using Solutions Enabler 7.6, and I'm just doing it by adding that mode flag. You can see it up there, mode v72. So if I just do it without the mode flag, I get what's expected in Solutions Enabler 7.6. I get the 4 characters in the string. If I add the mode flag, it looks like what it used to look like in 7.2. So it's a quick way to fix scripts that may have been broken due to the output changing in newer versions of Solutions Enabler if you were screen scraping. But if you're starting something new, you're starting from nothing and you have to develop a script, and you know that that script is going to exist for a while over time. It might be around for a couple of years or so, like you run a report on a daily basis or something like that. You can protect yourself from this, this brittleness by, rather than screen scraping the human readable output, use the XML output of SYMCLI. And pretty much any SYMCLI command has the option to output in XML mode. Just add the output XML_E flag, and you'll get a bunch of XML output. It's not pretty to look at, but it's really good for programmatically mining data out of. So here's just an example of that. And again, we're back to that same example where we're looking for multi-pool allocations. So previously, we were looking for the FX flags, right? So the FX flags in the XML output, they're not just all lumped together in one column where you have to match a specific pattern of text. They're actually broken out into separate XML elements inside that XML structure. So in this case, you see there's that device element at the top. There's going to be a device element for every device inside of the output of this command. And inside of that device, there's going to be child elements, and those child elements just basically describe attributes of the device that you're looking at the time. So the F flag correlates to the device emulation flag, FBA. The X flag correlates to the multi-pool allocation flag. So if multi-pool allocation is true, and the device is an open systems device, it's F, that's the device that we were looking for, right? And if we added, the developers added new flags, well, they're in there. You know, we see the X, the dot flag is persistent tracks, and the B flag is bound status. But the old script that we wrote to parse just for the F and X flags, it can just completely ignore those other elements because it's not shifting around the output. And even if you did shift around the output a little bit, we're looking for very specific elements. We're not looking for text patterns. So changing the XML output is not going to break old scripts. Does that make sense? Okay, so here is the same thing, but instead of doing this in a screen scraping method, we're doing it in Python and Python XML. So, and this is the entire script right here. So the first thing we do, highlighted up at the top, is we import a couple of Python modules. And modules, all they do is they bring some more functionality into the Python runtime. So we're importing subprocess. Subprocess is going to allow us to call external commands. So we're specifically going to use this to call the SYMCLI commands and capture the XML output. The next one is this elementary module. And the elementary module is an XML parsing module that is built into the standard Python library. So if you download and install Python 2.7.6 or Python 3x, you're just going to get this. You don't have to go and install it afterwards. And that's going to allow us to generate those XML objects that we can kind of explore later. Now I've got this function here. And this function, it really only does one thing. It accepts one argument, and that argument is a SYMCLI command. And what it does with that function is it adds the flag, the output XMLE flag, to the command, so you don't have to type it every time you call the function. And that just turns it into the XML output mode. It executes the command via that subprocess check output command bit right there. And it brings it into elementary and generates an elementary object for the entire command. And we name that object result, and then we return that result back to whoever called the function. So this next line here is where we're actually starting the script itself, and this is where we're calling the function, and we're generating an elementary object based on this command right here, the symcfglist tdevgb command. And we do that via the function that we just talked about, right? So what we end up with after this function runs is an object called tdevtree that represents the entire XML output of that one command. Then we're going to explore. We're going to explore that object. So the way we do that is I'm going to do it in a for loop in this case. There's other ways to do it, and I'll talk a little bit about those other ways in a bit. But what we're going to do is we're going to use a method of that elementary object. The method is the itterfind method, and the argument that we're passing to that method is going to be an XPath expression. And that's the XPath expression is right here, this Symmetrix/thin-devs/device. And what that basically does is going to navigate to a specific section inside of that XML structure. And if there are multiple elements that match that XPath expression, then it's going to iterate over all of those objects that match the expression. So in this case, there are, because what we're looking for is devices. So what we're going to end up with is every time we iterate through this for loop with that itterfind XPath expression, we're going to basically have a list, and that list is going to be all of the objects that correlate to all of the devices in the array that correlate to that command. Right? So now we're in the code block. So we're looking at a specific XML object that correlates to a specific tdev. And what we're doing is we're extracting some bits of information from that tdev, from that object. So the way we do that is, our variable in that for loop is device. So every time through that for loop, that variable device becomes the specific device object that we're analyzing at the time. So we use the find method on the device to find a specific element in that XML structure. You can see the pointers where we're looking here. And then we use the text method to just extract the text inside of that element. So the first one here, we're looking for the device name, right? So device name 2080 is the text inside of the dev name element. Likewise, we're looking for the emulation, which is going to be F for fiber channel. We're looking for the multi-pool flag. In this case, it's true. We're looking for the size. So we see this 1024 gigabytes. And then we move on to, and we've got all that information now into local variables. So we have name, emulation, multi-pool, and size. all in local variables, so we don't have to do any more XPath and expressions or worry about that object anymore. At the end, we're just going to do a conditional. So we're going to check to see if the emulation is F, so it's an FBA device, and the multi-pool track flag is true, then that's the device we're looking for, right? That is an open system device that has multiple allocations. So we just print the output, and we do that with the name. We print the name, and we print the size of that device, and we join it with a comma. So we just print it in a comma-separated value format. Does that make sense? Should I stop for any questions before I move on? Good? Okay. So, like I said before, that's a way to get a feel for which devices are or are not managed by a fast VP policy. And generally speaking, you're probably going to want every device in your box managed by a fast VP policy, especially if you're following best practices and everything is bound to the fiber channel pool, so your oversubscription rate is very high, and you're using allocate by VP policy, which allows you to spill over new writes into pools that have additional capacity. So you want everything to be associated to a pool so that allocate by VP capacity works, and you're able to spill over into particularly the SATA pool. So this is kind of looking for exceptions. It's looking for devices that you may have forgotten to put into a storage group and associated to a fast VP policy. And this is a little bit more comprehensive in that it's not just looking for devices that have that multi-pool flag. It's actually going to look for devices that are in a storage group that are actively associated to a fast VP policy and just prints those that are exceptions from that rule. So really, the only command we need to do this is the symsglist command. It actually has all the output we need. So let's walk through it. And actually, this code is all available on GitHub, so if you want to download it, feel free. I don't know if you want to take screenshots or whatever. But the streaming video and the PowerPoint will be available as well if you don't happen to get these links. But the first link there is the actual script that I'm going to go through here. And there's two of them. One is the one where I'm going to use the elementary module that I already talked about. Another one is going to use this LXML etree module. And the LXML etree module, it's not built into the Python standard library. So you won't just get it when you install Python. You'll have to download it separately with pip, and it'll have to compile. But it's faster than elementary. And it has full support for XPath expressions, which can be actually really powerful. And we can replace a lot of the for loops and the nested for loop stuff with just a couple lines of more advanced XPath expressions. I'm going to go through just elementary here because I figured it's more easily accessible, but I at least have the code for LXML available on GitHub. This second one here is a more comprehensive version of this report. The second one will print every TDEV in the system. It'll print the provision capacity, the written capacity, the allocated capacity for every TDEV, and what pool that allocated capacity is in, what storage groups the TDEV is in, the complete list, what fast VP associated storage group the device is in, what policy that is associated with, and what the percentages are allowed for that device in the policy. And then another one is completely different. This is a storage group capacity report. So this will give you, by storage group, a quick report on the provisioned, written, and allocated capacity as a whole inside that storage group, kind of a summary. But the one I'm going to go through is this fast list TDEVs, which prints just the exceptions in a relatively straightforward way. And there's two screens in the script. But the first thing we're going to do here, like before, we do our module imports. So we import subprocess again. We import elementary again, but we do it a little bit differently this time. So there's two implementations of elementary. There is a C implementation of elementary. That's the one you want if it is on the system because it's faster. So I'm going to try to import C elementary first. If that is not on the system, it's going to raise an exception, and we're going to go into that exception block here, and I'm going to fall back to just using the elementary module, which is implemented in Python. Still has all the functionality, it's just not as fast. I'm also importing this argparse module, and this is another module that's built into Python that will allow you to easily define command line arguments for any Python script. And really, I'm only going to define one, but it gives you this built-in help mechanism. So, when you run the script name -h, it'll show you all of the arguments that are available and what those arguments do. And it's just you get it kind of for free if you use the argparse module. It's really easy. Next thing I've got is the SYMCLI gentry function. This is the exact same function we did before, right? It just takes a SYMCLI command, captures the XML object, or XML output, I should say, and generates the XML object and returns it to the caller. This next bit is where we're actually defining and parsing those CLI arguments. So what we got is defining the parser. We give a description for what the script does. You'll see that in the help output. we define one argument. That argument is just going to be the SID, the same syntax that you would use in a normal SYMCLI command, like symdev minus SID list or whatever. We have that now defined in this script. And then we're going to parse the arguments. And we do that by doing the parse args method of the parser that we defined. And that goes into the args object, the args variable. So anytime we want to get the serial number that the user entered on the screen or on the command line, we just reference args.sid, and that will give us the serial number that the user entered. Next thing we're going to do is we're going to use that SymCLI gen tree function again, and we're going to capture the XML output and generate an element tree object representing that XML object of this command. So the command in question here is symsglist minus v. And we're passing the serial number into that command as well, so because you're targeting one sim, not all of the sims. And that is just going to be named sgtree. So that's our top-level object that represents all of the XML output of that particular command. So guys, now we're moving on. So the way that I'm doing this is with a Python built-in object type called a set. And a set is very similar to a list in Python or a list in Perl or Ruby, for that matter. The difference is, when a list, if you have, say, elements A, B, C, C, and you put A, B, C, C onto a list, you're going to end up having A, B, C, C. Sets are inherently unique. All the elements of this set have to be unique. So if you add A, B, C, C to a set, once you add that last element, that second C, it's not actually going to do anything because the C is already there. So you could kind of emulate this with a list. You could test to see if an element is already there before you add the element to the list. But it's easier just to use a set. The other reason it's easier for this application is because sets have these built-in comparison mechanisms where you can take one set and subtract it from another set and see what the differences are. And there's lots of other comparison mechanisms that sets have. So what we're going to do here is I'm going to have this all tdev set, and ultimately I'm going to populate that with a list of all the tdevs that are in any storage group in the system. So that's going to be the big list, all the tdevs in the box, basically. Then I'm going to take this fast tdev set, and I'm going to populate that with only the tdevs that are in a storage group that are associated to a fast VP policy. So that's going to be the smaller list, right? Just the fast managed tdevs. Then at the end, I'm just going to subtract fast tdevs from all tdevs, and I get my list of exceptions. I get my list of devices that are not managed by fast VP. So everything in the middle is just about populating the set. And this is the bit where, I was talking about how you could kind of replace some things with more advanced XPath expressions. This is the bit that you could replace. This actually whole section of the script could be replaced with 5 lines. But trying to describe those 5 lines in this kind of format is a little difficult. So I'm just going to do it this way. So first we're going to iterate again. We're going to start a for loop again. So in this for loop, we're going to iterate against all of the storage groups in this system. So here's the XML output of that command. And we've got an SG element, a parent SG element, for every storage group in the array. So we're going to iterate over every storage group in the array. And every time we iterate over that list, we're going to be looking at one particular storage group, right? So now we're in the code block, and we're going to start another loop, another for loop. So we got a nested for loop. And this nested for loop is for a particular storage group. We're going to iterate against all of the devices that are a member of that storage group. And we do that the same way, right? We're now using our SG object that we're iterating against, which is the variable that starts, that changes every time we're through the top level for loop. And we use iterFind again. And the XPath expression we're using here is devs/device. So you can see where that points to in the output here. It's just all of the devices that are members of this particular storage group. And we're going to iterate over all those devices. So here we're getting into the code. And the first thing we're doing is we're just extracting information out of some of the elements associated with that particular device. The first thing we extract is the device names. So on the screen, you can see 2 device objects, right? And we're extracting, you can see there's 2 names associated with those objects. There's, of course, going to be many more than just 2, which just gives you an example. So we've got the name. We've got the name in dev_name, and that's going to be names 2639 and 2641. Then we move on, and we have this all tdevs.update, and that just adds that name onto the all tdevs set, the bigger set, right? So if that device already happens to be on the set, it's okay. It just won't be added. And it's not going to raise any errors or anything like that. It's just not going to add any duplicates because it's a set. Then we're moving on, and we're doing a test. We're doing a test to see if the device that we're working on right now is in a storage group that is managed by a FastVP policy. And there happens to be an element under the storage group that tells us whether this storage group is or is not associated to a policy. So we just check that. So we do sg.find and do our XPath expression there, sg info fast policy, and that points to that element up there which says no. So this storage group that this device is in is not associated to a FastVP policy. If it were a yes, then we would execute the code right below there, and we would add that device to the fast tdev set. But because it's a no, we don't execute that block, and that device does not get added to the fast tdev set. So basically, after we iterate, we execute that entire nested for loop completes. We'll have a fully populated all tdev set and a fully populated fast tdev set, and we move on to the bottom where we just print our report, right? And it's similar to before. We take our all tdev set, we subtract the fast tdev set. That gives us the exception, the list of devices that are not in a storage group managed by FastVP. We print those devices, and we just separate the print by joining them with a comma and a space. So what your output ends up looking like is this. So your command is fastlist underscore tdevs.py. You specify your SID 1276, and your results are all of those tdevs that are not associated to a FastVP policy separated by a comma and a space. Does that make sense? Any questions so far? Okay. So that was basically the XML output piece. I've got a few additional tips for scripting a bit later here. But just some kind of key takeaways for scripting in general. Of course, prior to scripting, know what your outputs are going to look like. Before you start screen scraping stuff, you need to know what the patterns are going to look like that you're going to try to match. Likewise, if you're going to start parsing XML, you need to know what the XML structure is going to look like. Where are the members inside of a storage group? What level do they sit in? What are their parents? What are their children? You can just do that by executing the command with the output XMLE, redirecting it to a file, and then just open it up in an XML editor, and it'll highlight them for you, and you can see what the structure of the XML looks like. Also, check for additional functionality. Check to see if there's not something that's already built into SYMCLI that can do what you want to do, so you're not reinventing the wheel. Check Unisphere, check SRM, ProSphere, ECC, whatever you happen to have in the environment that can do this kind of stuff, just make sure you don't already have something that can do it. When you're just dealing with ad hoc scripts, you're going to run something a couple of times. Screen scraping is totally fine. It's really easy to implement, so you might as well do it that way. But when you're implementing something that's going to be around for a while, or a port that's going to be important and is going to run for years, use the XML output if you can. Some other tips. So if you're making changes with a script, say you're provisioning storage, or you're doing a time finder clone refresh or something like that, where you're actively making changes inside of a script, you're going to want to check to make sure that the change was successful before you move on to other things. One way you could do this is like anytime you make a change, it's going to print on the screen, time finder clone recreate was successful. You could parse that. The better way to do it, though, is every SYMCLI command is going to have a return code. And universally, if the return code is 0, it means the command executed as expected. It worked. If it's a non-zero, then something weird happened. We don't know just offhand, based on the number alone, whether that was catastrophically weird or just kind of an anomaly. But if you look in the Solutions Enabler reference guide, there's a table, and that table will show you all of the possible return codes and what they mean. So if you're doing like a time finder refresh or something like that, you'll want to look in that table and see all of the return codes that are applicable to time finder, and have some logic built into your script that would deal with those. Because you don't want to, say, have a process that would do a recreate and then an activate and then a mount on a backup host and start your backup. If the recreate didn't work, you're not going to want to keep going. You're not going to want to try to activate. You're not going to try to mount, because you're just going to be doing nothing, or at worst messing stuff up. You want to have some logic in there that can deal with unusual situations. The way syntactically you would do this inside of Python would be in a try and an except block, just like we did when we were importing that C elementary and then the elementary module before. So what we're going to do is we'll try to execute this command, symreturn1. And literally the only thing that command does is returns a return code. So that's just the only thing that's going to do is return a return code of 1, just as a demonstration. So if that was symreturn 0 and we were returning a return code of 0, we would just execute that code, that subprocess check output code, and be done. If that returned a non-zero, it would raise an exception, and we would go into this exception code block. And the only thing that the exception code block does in this case is it just prints out the return code. So of course, you'd want to do something more useful, applicable to the thing that you're trying to do, based on the return code reference list. But this is the syntax for doing it. Some other tips, a lot of times, particularly when you're dealing with data services, like copy services, you're going to want to start a copy, like a time finder incremental recreate, or an SRDF sync or something like that, and then wait for the copy to complete, at least partially wait for the copy to complete. You don't necessarily have to wait, but you might want to wait, right? You could activate a time finder clone immediately after recreating it, and it'll use copy on first access where necessary. But you could also kind of make it use kind of the old SymMirror semantics, where it waits for the full differential copy to complete before you do the activate and do your work on the clone. So if you wanted to do that, there's a lot of, you could write your own polling mechanism to, periodically check to see what the status is of the copy and wait for it to go into synchronized mode. But there's actually built-in stuff to SymCLI that'll just do that for you, so I'd encourage you just to use it. So as an example, for a clone, like say for a clone, the example I just mentioned, you want to wait for the clone pre-copy to complete before you activate the clone session. You'd use the symclone verify minus pre-copy minus cycled command, and that checks to see whether the first pre-copy cycle of the differential recreate has completed before you move on to the next task. We're also specifying an interval, which is a polling interval, how often we wait in between polls for status, and a count, that's the C. So 60 times we're going to do a poll, and we're going to wait 60 seconds in between each poll. So we're going to wait for an hour. If that pre-copy cycle completes within the hour, then this command is just going to exit with a zero return code. If it doesn't complete and the timer has run out, then it's going to exit with a non-zero return code. So that gives you a way to determine whether you do or do not want to move on with this. In this case, I'd say probably move on, but it's up to you. Same deal for SRDF. If you want to wait for an SRDF established to complete, that same functionality exists for things like SRDF and Open Replicator and all of the data copy services in the SIM. There's also some lesser-known SymCLI commands. I don't think a lot of people tend to use these or even know they exist. And these are kind of the SRM commands. So it's about resolving northbound, southbound relationships up and down the storage stack. And some examples of this are the SymVM command. So this is virtual machine hypervisor oriented, and I'll give you some examples of that one, where you can kind of drill down to see what one is on this data store, that sort of thing. So it's equivalent to like the VSI, which has the top-down view. This has the bottom-up view, just like kind of Unisphere does as well. There's the SymVG, SymLV, SymPart, SymHostFS, SymRSLV. Those are all host data object oriented. So it's about resolving things like volume groups and logical volumes and partitions and directories and file systems and even files down to the underlying LUNs that those objects reside upon. And there's also the RDB. So this is about relational databases. So Oracle, SQL, MySQL, Sybase. We can connect into those instances with authentication information and resolve things like table spaces and databases and schemas and extents and that kind of thing down to the underlying storage that is supporting those objects. And all of these commands support the XML output as well. So it's great for reporting higher up in the stack and not just in the storage domain itself. So just as a quick example of the SymVM command, so before you run the SymVM command, you have to provide some information, some authentication information to Solutions Enabler so it knows how to authenticate to the ESX server. And what you're providing here is a username and password that are local to the ESXi host, not a vCenter username and password, but a local username and password. So the syntax for that is here, symcfg auth VMware add, our host name, our username, and our password. And that data gets stored in an encrypted file on the server that has Solutions Enabler installed. So you don't have to enter it every time. Then we run the SymVM server, and then the IP address show, and we can optionally use this -out XMLE flag, so that'll dump the output, of course, into XML format. So if we just kind of look through this, you see we get some ESX server basic information, right? We can see that this is a ESX51. You get the build level, number of CPUs, number of memory, the host name, that sort of thing. We get device NAA to array mapping information. So we can say that, see, this NAA name corresponds to this array. Diving deeper into it, you can, and this is, I think, probably the most useful bit of the output here. You can get data store to LUN mapping. Even if it has more than one extent for a data store, you can get the LUNs that are associated with those extents. And this happens to work on both VMAX, Symmetrix VMAX and Clarion and VNX. So here you're seeing some VNX data. You see that this data store Dave Denise test is on a VNX, VNX 1433, and it's LUN 3. Likewise, you see another one down there. And moving on, this is the last screen of data from this command. And in this one, you see all of the VMs that are actively running on that particular host and some information about the VM at the top. See, its name is Mercury. It's running Linux. You can see some basic stats about what virtual hardware it has. And if the VM is using any RDMs, you've got any RDMs presented to the VM, you see the RDM mapping information here. And you can actually provision RDMs through SymVM as well if you're using RDMs. I don't know how many people still are doing that. Another little useful tidbit about Solutions Enabler, if you aren't aware of it already, natively by default, if you install Solutions Enabler, you'll get the SymCLI and the SymAPI installed on one server. But you can actually split these apart. So say you've got a web server that is periodically running a report or something like that and producing HTML output. But you don't want to give that web server fiber channel access. You don't want to give it gatekeepers and in-band direct access. It only has IP. One option for handling that, well, one would be to present iSCSI gatekeepers to it and just don't do the client-server mode. But I think a better one would be to use client-server mode with SymAPI. So you separate the SymCLI and the SymAPI, and the SymCLI just talks over native IP to a SymAPI server. It's port 2707 by default. It can do OpenSSL or just plain text. And basically, once you set that up, any normal SymCLI command that you would run in a default installation will just work in a networked configuration. And just the way that you would set it up. There's a file on the Solutions Enabler client. There's the file name right there. You put in a service name. You put in the IP address. You put the port. You specify the security type, OpenSSL, plain text, or both. And actually, by the way, this was actually subject to the Heartbleed bug up until recently. So if you do use this, just upgrade to the newest version of Solutions Enabler, and that's fixed. There's no Heartbleed bug anymore if you run the latest version. So set these two variables. So SymCLI connect type equals remote. That just says operate in client server mode. And then SymCLI connect is going to refer to the service name that we specified in that netcnfg file. Once we've done this, all of our local commands will just work over the IP network in remote mode. It'll be a little slower, but they'll work. Another cool thing with Solutions Enabler that you may or may not be aware of is offline mode. And this is particularly useful for employees and partners. I don't know if we have any partners in here. But I use this all the time. And so what you can do is you can ask a customer or anyone to send you their SymAPI database, just a file that exists on the Solutions Enabler install. And if they send that to you, you can load Solutions Enabler on your laptop or on a VM. That's what I do. And you can basically point the Solutions Enabler SymCLI client to that offline SymAPI database. And any read-only command will work, including the XML output. So you can parse configuration data out of any customer's SymAPI database in an offline manner. I have actually told customers to do this before, like customers with geographically distributed environments where they don't have RDF connectivity between all their arrays, and they don't have like SRM or something, but they want to get a centralized report. I'll tell them to just on a daily basis kind of centralize all those SymAPI databases to one central location, and then one by one run your reports against each of those SymAPI databases to get the data out. It's going to be slightly stale data, but it's relatively up to date depending on how often they push the files out there. And I think this is the last one, just some environment variables that are useful for scripting. These first two are related to locks that you may encounter in a script while executing SymCLI commands. So there's two types of locks that you would commonly encounter. The one is the SymAPI lock. So when we're making some sort of config change or like we're making a device read-write from not ready or vice versa, we're going to temporarily lock that SymAPI database so that we don't step on each other inside of the SymAPI database. And if a command is run and there's a lock, then that command is just going to fail. But if you set this variable here, this waitOnDB variable, if that second command comes in and encounters a lock, it's just going to sit back and wait until the lock is released, and then it'll execute. So in a script, that's pretty important. You don't want your script to fail because you encountered a lock. Likewise with waitOnGatekeeper. So this is one where if all of the gatekeepers that you have assigned to the host that you're running the script on are locked by other commands, then by default, if this other process comes in, wants to use a gatekeeper, they're all locked, the other hand's going to fail. So this is the same deal. This will just wait for a gatekeeper to be available. Once one's available, it'll keep going. So it just prevents your scripts from breaking due to locking. SymCLI no prompt, if you're running like a symconfigure commit, or you're doing a symdev not ready, or making some kind of change on the system, you're generally going to get a prompt that says, are you sure you really want to do this? Yes, no. You could use the NOP, no prompt flag on every command to get by that, but you could also do it globally with this no prompt environment variable. This other one, SymCLI full name, if you have long storage group names or long device group names, long consistency group names, you might see that when you do a SymGG list or a SymCG list or SymSG list, those names are truncated with an asterisk, so you don't see the full name in the output. You will see the full output in the XML output, but you can actually set this environment variable and make it so you'll see the full output in the SymSG, CG, and DG commands. They won't be truncated if that environment variable is set. And there's lots more of these variables, so if you want to see a list of all of the available variables, just run SymCLI env, and it'll show you the variables, what they do, and their defaults. Do you have a question? If you set it inside a given shell or command prompt, it'll be just local inside that one command prompt. If you set it like on my computer, or if you set it in your login script, then it'll be universal every time you log in. Is that what you were getting at?
Yeah. What is the variable for
Oh, okay, I'm sorry. It's 1. Yeah, so 1 is what you would do to not truncate. I didn't catch your question. I'll have to fix that. And to see a list of all the environment variables that are available in a quick list format, SymCLI env will list all the variables and a quick description of what they do and their default values. And then if you have defined any variables, like if you've defined SymCLI full name equals 1, which is deviates from the default, then if you run a SymCLI minus def, it'll show you all of the SymCLI variables that have deviated from the defaults, things where you've changed them. If you had more gatekeepers, would it speed up? In what, client-server mode, you mean? I think the latency in that case is more going over the network rather than a lack of gatekeepers. So it might speed you up if you encounter locks, like if you're running into locks frequently, then having more gatekeepers would.
So where are the places that we have locks, right? So do we have locks on the array itself?
You do. You do.
And also we have the one on the API server.
And on individual devices and on gatekeepers, yeah. So the lock that you'll get on the array itself is typically going to be a config lock, and there's no way to get around that one. That's either a case where you've got a bin file that's pending, and we've got your bin file offline and going through CCA, and you're locked while we're doing that. And we've made improvements there, so we can do like hardware lockless adds, where if we're just adding hardware, we don't need to lock the system. And if your CEs aren't doing that, you should look into it, because they should be doing it. And we're trying to kind of communicate that more in the field. But there's not really a whole lot you can do about those locks as far as waiting goes. Yeah, these are the main ones that you'll often encounter during scripts, though. But yeah, that was it. So we're just into questions now, if you guys have any questions.